last chapter of this unit is chapter 8. It's called An Introduction to Metabolism, and this is when we start getting into actually all these things we've been talking about, all the chemistry, actually seeing it come to life and things actually interacting with each other and how that happens. So your textbook talks about how cells are miniature factories and everything's carried out by enzymes. Remember that enzymes are proteins that do a job. And so this chapter is about how that happens, because by definition, metabolism is the sum total of all of the chemical reactions in your body, or in a body. So this chapter is about how that happens. So all these enzymes need energy, or all these things, something needs to power all these reactions. And so that's where the beginning of this chapter is, how this energy happens. So we're going to talk a lot about energy in this chapter. So that says some organisms even convert light to energy, or energy to light, as in bioluminescence. So those are little tiny microscopic living things that create light. So the first section is called An Organism's Metabolism Transforms Matter and Energy Subject to the Laws of Thermodynamics. So there's these two laws of thermodynamics, and we're going to discuss what those are. But first, like I said before, metabolism is the total of all chemical reactions that happen inside of a living thing. And this is an emergent property of life that arises from interactions between molecules within the cell. So remember that emergent properties are things that appear as you move up a hierarchy. So think about, there's all these molecules inside of us, and then all those molecules together will form a cell, and all the cells together will form a human being. And so metabolism is a characteristic of an organism that we can't talk about with molecules alone, because two molecules doing a reaction is not a metabolism. You need to have an interaction of an entire organism to have a metabolism. So that's what emergent properties means. And metabolisms are really complicated. So it's not just really simple and straightforward. It's the interaction of a bunch of different chemical pathways and how they work together. So it usually, a metabolic pathway, that's what we talk about, that language, metabolic pathway, starts with a particular molecule, which is altered in a series of steps and then ends with a product. And sometimes these steps can take different paths, and that's why it's not one straight thing, why it's a roadmap that goes in a lot of different directions. And each step is catalyzed by a different enzyme. So this is where our enzymes come into play. They are causing all of these chemical reactions. So here is one metabolic pathway. We start off with A, whatever A might be, and then A is altered in a series of steps and ends up in product D. And each of these steps is catalyzed by an enzyme. So it's not just A going straight to D. We have A that gets modified by enzyme 1, and then we have B at the end. And enzyme 2 modifies B to C, and then enzyme 3 does the final step, going from molecule 3 to molecule C to molecule D. So that's how we go from A to D. It takes a bunch of different steps. And each of these steps is a part of a metabolism, so this is what we call a metabolic pathway. Your textbook comes up with the analogy that says, just like a stoplight regulates the flow of traffic, enzymes regulate the flow of metabolic pathways. So let's say enzyme 1 works really, really quickly, but enzyme 2 works really, really slowly. This pathway is going to be pretty slow, because it can only work as fast as enzyme 2 can convert B to C. So there's two different types of pathways, the kind that build up molecules and the kind that break down molecules. And the first kind is catabolic pathways. And catabolic pathways break down larger, more complex molecules into smaller pieces, and as they do this, they release energy. And so cellular respiration is one of the most prominent catabolic pathways in all of life. And this is when enzymes break down glucose into carbon dioxide and water, and as the steps go on, it releases energy. That's where all of our cells get energy from, is cellular respiration, and that is a catabolic pathway. This is the reverse of anabolic pathways, which are pathways that build up complex molecules from smaller ones. So think of this as anabolic steroids. Anabolic steroids are the ones that like bodybuilders or old professional baseball players take to get huge muscles because they're building up their muscles. So think of it that way. Anabolic is building up. And so this is how glucose is made. So we start with carbon dioxide and water, and we put in energy to get larger, more complex molecules. So an example that this gives is the synthesis of proteins from amino acids, and is an example of an anabolism. So we start off with all these little amino acids, and we have to put in energy to make those peptide bonds. And then at the end, we have a protein. And then bioenergetics is the study of how organisms manage their energy resources. So where do you put in your energy? What kind of pathways do you use to break down your energy or to build up your energy? That's a pretty straightforward thing. Bio would be of life, and energetics is energy. So by definition, we've been talking about energy, and energy by definition is the capacity to cause change or to do work. So how much capability do you have to alter that molecule or to push that boulder up the mountain, if we're talking about it that way? And so energy exists in various forms, and some of these can do work. Not all of them, but some of them can. So there's many different kinds of energy. The first one is kinetic energy, which is energy of motion. So anytime anything's moving at all, it has kinetic energy. And down to the most very, very basic level, heat is the kinetic energy caused by molecular motion. So remember back to chemistry in chapter 2 that all molecules are in constant motion, right? All atoms are constantly moving, all electrons are constantly moving, so they have kinetic energy because kinetic energy is the energy from motion. So heat is just molecular movement. That's what the energy from molecular movement. That just random energy that they're always moving around. And potential energy, this is the opposite of kinetic energy, is energy that matter possesses because of its location or structure. So it's the potential to do work later. So for example, I'll come back to this slide. For example, this is the picture that your textbook gives. So this girl right here is expending kinetic energy because she's climbing. So she's in the water, she's climbing up this pole, or climbing up this ladder, so she has kinetic energy. As she climbs up the ladder, her energy is being changed to potential energy because now she's taller, she's on this platform, so she has the potential to jump off. That's potential energy. This person up here, this diver, has even more potential energy because he's even higher. So as you climb, you're putting in your energy in the form of kinetic energy, and you're gaining potential energy. And so this diver right here is diving off. So as he's jumping downward, his potential energy is being transformed into kinetic energy, the energy of movement. So that's what it means by because of its location or structure. So as you climb higher up, you have more potential energy. Structure meaning sometimes chemicals, molecules can store energy as well, and that's potential energy also. So we call that chemical energy. So chemical energy is the energy available for release in a chemical reaction. So the molecule glucose has a lot of potential energy because it stores a lot of energy that can be used later in a chemical reaction. And it's important to know that energy can be converted from one form to another. That's possible, happens all the time. So again, here's that picture that we were talking about. So low potential energy down here, high potential energy up here. So I just said that energy can be transformed from different forms, and thermodynamics is the study of the transfer of energy. So thermo means heat. Heat is just a form of energy, and dynamics means changing. So thermodynamics is the study of energy changes, basically. So we're going to talk about systems. Like it says an isolated system or an open system. And this is just talking about whatever is interacting. So by definition, just to give, it says the word system is used to denote the matter under study. So whatever we're looking at, that's the system that we're looking at. It's usually going to be a process or a reaction. That's the system. And if the system is isolated, that means it does not interact with the rest of the universe. It's only interacting with what is happening inside the system. It's different than an open system, which has the potential to interact with the rest of the universe. So we either have a closed system and its surroundings, which it's not interacting with, which is the rest of the universe, or we have an open system, which can get energy and materials into and out of it from the rest of the universe. So an isolated system would be the liquid in a thermos, totally isolated from its surroundings. It's not, the heat is being kept inside, in theory, and it's not gaining or losing heat to the outside. Whereas an open system would be like a coffee cup. It's really easy for heat to escape because it's not being held inside. And it's important to know that organisms are open systems. So we are constantly putting in energy and losing energy to the rest of the universe. We are not closed systems. And there's 2 laws of thermodynamics, okay? So there's 2 important things to know about how organisms and all things in the universe, not just living things, exchange matter and energy. So the first law of thermodynamics says that energy can be transferred and transformed, but it cannot be created or destroyed. So this is called the law of conservation of energy. So you cannot create or destroy energy ever. The same amount of energy is in the universe now as it was at the very, very origin of the universe, will be at the very, very end of the universe. However, we can change forms that the energy is in. So we can change it from light energy to chemical energy to kinetic energy. We can easily, to heat, we can easily change energy forms, but we're never creating or destroying energy. So this is why you need to eat, because your body can't create its own energy. It needs to get energy from the glucose stored in the food that you're eating. So that's the first law of thermodynamics. The second law of thermodynamics says that even at every energy transfer, you are losing some heat. So anytime you transfer energy, increases the heat that you're putting off into the universe, and also increases what's called the entropy of the universe. This is a new word. I'm not sure if you guys learned it in chemistry or not. But entropy means disorder. So every time we transfer energy from one form to another, we're making the universe a little bit more messy. And the tendency of all things is for entropy to increase, because it's so much easier for things to be disordered than ordered, because keeping things in order requires more work. So here is a bear demonstrating the first and second law of thermodynamics. This guy is eating a fish because he needs to get energy. He can't make his own energy because energy cannot be created or destroyed, but it can be transferred in form, so he's getting chemical energy from the fish. His body will break down the glucose and the fat stored inside of the fish and use it for itself. The second law of thermodynamics says that as this bear transforms chemical energy into kinetic energy to run through the water, some energy is lost as heat. So in every energy transfer, some energy is lost as heat. And that increases the disorder in the universe. So let's talk a little bit about what I mean by disorder. So in a really large molecule with a lot of bonds, that's very ordered. It's one large thing. There's not much movement happening inside of that molecule, and it's very structured. And it probably stores a lot of energy. So as we break it down and release the energy, now that molecule is a bunch of little molecules who are going to bump into each other and move around. So that's more disorder inside of the universe. And so we need to do that all the time. We need to break down large organized molecules to get energy out of them. So we break down glucose or glycogen into smaller molecules, and ultimately some heat is released and the entropy of the universe is increased. And spontaneous processes are the ones that can occur, without the input of energy. They happen on their own because they release energy. We don't need to put in energy. They can happen on their own. This does not mean that they happen quickly. It just means that they will happen on their own. And when this happens, they increase the entropy of the universe. So for a process to occur without energy input, it must increase the entropy of the universe.